if you ever wondered why when you're playing a dungeon crawler game that you don't get stuck in an infinite loop or the game just arbitrarily ends when you're barred while you're slaying a boss or getting a key, well, the secret is graph theory, really. The way those rooms are generated and why they're random in the first place all depends on how much you know math and how much you know the cool part of math, which is graph theory. And here we have one of the best examples of graph theory interacting with gameplay, which is The Legend of Zelda, the old Legend of Zelda, not the new and shiny one right now, but the old school one, which was the perfect dungeon crawler. It generated rooms randomly and allowed the players to go and do objectives in each room. And the goal was to always get a key, slay a boss, and move forward until you reach the end, which is the end level, or as in the Legend of Zelda, the end boss. And so you'd go into each room like this one. And each room would be randomly generated. And this would be done by the Dillonite triangulation, which is used to generate the room layout by connecting the centers into a planar graph. And then it ensures that there's no overlapping in edges, so there would be no overlapping in any of the edges, so hence there would be a maximization in spatial efficiency. This means that in each room, not only will it be unique than the other rooms, but you won't really enter the same room twice, and you won't find it interconnected in such a weird way that you don't know what to do. Mainly, the way to brawn the triangulated graph is using a minimal spanning tree via the Kruskal's algorithm, which we'll be talking about more in our paper, but it mainly just is used to guarantee that there's connectivity while minimizing the edges. And as you can see here, this is a randomly generated dungeon. Well, more than one dungeon, but you get the idea. This is using all what I just said here. It uses the triangulation of Delaunay's and the minimal spanning tree via Kruskal's algorithm. Each one of these points is a dungeon, and it uses it so it makes sure there's no edge overlapping between any of them, and you can walk through any of them. And we use also a directed acyclic graph to make sure there's no cycles. So you'd have the spawn, which you would spawn in, and then a room next to it, and then another room, and so on and so forth. But hence there's a problem if it's randomly generated. I said there's a boss, and it's mainly the end room. What if the boss room gets really generated while you are just in your spawn room and it becomes the next room you go in? Won't be such a fun game then. But to fix this problem, actually, we do use the acyclic graphs. And we use also Minger's theorem to ensure that there's K connectivity in the dungeon graph to prevent soft locks. And if you go through the boss room without a lock and key, you wouldn't be able to progress because you wouldn't be able to kill the boss and go on. So this is mainly the whole part of our project here that we're trying to say how it works and how it's really effective in what it does and how it made generations of gamers really play those games and how it's cool when it's applied to game design. So you'd have the whole dungeon be generated like that, and it uses bosses and puzzle and loot, and at the end you'd have something as beautiful as what you're seeing right now, something that is as much enjoyable as it is complicated and cool.